Hello everyone, I'm J Wildberger. So we'd like to finish this little foray into complex numbers by talking about factoring polynomials into linear and quadratic factors. So what's going on here is that with the complex number story, we get a somehow deeper understanding of the whole problem of factoring polynomials that we learned in high school. So a good place to start perhaps is having a little bit of a more in-depth look at factoring some really simple polynomials, which were quite important ones. Ones of the form z to the n minus 1. And here's scientific workplace again, and I've already put in these polynomials, z to the n minus 1 from a 1 to 10 here in a little matrix. And actually that allows me to factor all of them all at the same time. So here is the factorization that this program easily can do. And I want you to have a look at this. It's kind of interesting. Of course, there's z minus 1 is a factor of all of them. And then there's these other factors. If the exponent is a prime, then we get just a whole sum like this 1 plus z squared all the way up to z to the prime minus 1. Same thing here with z to the 5. And if I scroll down a little bit, and you'll see the same kind of thing can happen with the higher powers. Let's do that one as well. Factor all of those. Okay, a little bit more complicated here. So it's actually quite a rich story of trying to understand what these various factors are. In fact, in higher algebra, these factors actually figure quite importantly in sort of algebraic theory called cyclotomic, connected with number theory as well. But we're just interested in this problem of trying to understand, how do you factor polynomials. And the kind of factorization that the computer is giving me here, sort of very, very quickly, is great, but it's not really as deep as we can go. We can go in a deeper way. And that's by exploiting the fact that the fundamental theorem of algebra actually allows us to factor any polynomial, in fact, into a product of linear factors. Okay, so if we go to the complex numbers, then all of these polynomials will factor further. But remember that qualification I told you about last time, that actually that's really more of an approximate statement, not really an exact theoretical one. So we want to go further on that topic today and exploit the fact that something especially particular happens when we have real polynomials. Okay, so we'll just start here. Let's go to our screen here. So let's start by saying that start with black pen. Okay, so a polynomial, say f, is a0 plus a1z plus all the way up to a n z to the n is a real polynomial if all of these coefficients, if a0, a1, up to an, all belong to real numbers. Okay, so, for us, real numbers are actually more like either rational numbers or finite decimals. But, if you're able to contemplate infinite decimals, okay, then you can include that as well. Okay, so that's a special kind of polynomial. In fact, these are the polynomials that you're more likely to come across. Now, they have a particular property because of the following important theorem. That if f is a real polynomial, and say alpha, a complex number, is a 0 or a root of f, 0 or root of f, and I remind you, i.e., that means that f of alpha equals 0, then the complex conjugate of alpha, alpha bar, is also a 0. That is, f of alpha bar also equals 0. So that means that if you have a real polynomial, whenever you have one zero, you automatically had a second one, namely its complex conjugate. We'll note that if alpha is itself a real 0, then of course alpha bar is just equal to alpha, and so we don't get anything new. But otherwise, the non-real roots come in complex conjugate pairs. I guess we don't need a bracket, okay? So that's complex conjugate pairs. So how do we prove this? Well, we make the following observation, that we know that alpha is a root. So that alpha, when you plug it into f, you get 0. That means that, say, remember that f is equal to this polynomial up here. We're starting with a0 all the way up to a and z. So that means when we plug in alpha for z, we get a0 plus a1 alpha plus a2 alpha squared all the way up to alpha to the n all the way up to a sub n times alpha to the n. That should be equal to 0. Okay, now take the complex conjugate of both sides. Take complex conjugates. And we need to recall, to do that, we need to recall a couple of basic facts about complex conjugates. That if you have two complex numbers, say z plus w, and take the complex conjugate of the sum, then you get z bar plus w bar. And if you similarly take the complex conjugate of a product, say zw complex conjugate, that's the same as the complex conjugate of z times the complex conjugate of w. Okay, and maybe we should also just note and that a bar equals a if a is a real number. Okay, the complex conjugate of a real number does not change it. Okay, so we can then take the complex conjugate of this equation up here. What do we get? We get a0, the complex conjugate of that, plus a1 alpha complex conjugate of that, plus a2 alpha squared complex conjugate of that, all the way up to an alpha to the n complex conjugate of that, equals the complex conjugate of 0, which is 0. But now, the AIs are all real, so they satisfy this property, that their complex conjugates are themselves. And also, well, these products of complex conjugates, they separate according to this rule here. So this becomes a0 plus, now the complex conjugate of this is the complex conjugate of a1, which is itself, times the complex conjugate of alpha, which is alpha bar. And the next term, the complex conjugate of a2 is just a2 itself, because we're assuming it's real. And the complex conjugate of alpha squared is its complex conjugate. All the way up to an times the complex conjugate of alpha to the n equals 0. But one more fact is, it's a kind of an extension of this one, but also if we take a to the, say, k and take the complex conjugate of that, that's the same as a complex conjugate to the k. Okay, so this becomes, we get a0 plus a1 times alpha bar plus a2. This thing here, this alpha squared complex conjugate, is the same as alpha conjugate all squared. And all the way up to an alpha conjugate to the nth power. And all of that equals 0. And now when we stare at this equation, well, this just tells us, therefore, that the function f evaluated at alpha bar equals 0. Okay, and that proves the result. It proves that if f is a real polynomial and alpha is in C, is a 0 or a root of f, then also its conjugate is also a root. So typically what happens then for real polynomials, the zeros look something like this. Okay, so here's a kind of a possible picture of the zeros of a real polynomial in the complex plane. There's 1, there's I. Okay, it's maybe in red. So there may be a few real zeros, okay? These are points on the line, which are real numbers. So these are real zeros of f of z. That means they're real numbers that when you plug in, you get 0. And then there will also be complex conjugate pairs. Maybe we'll do a different color. Maybe this number is a 0. Then also its complex conjugate will also be a 0. Maybe this number here is a 0. Well, then its complex conjugate will also be a 0. Maybe this number here is a 0. Then its complex conjugate will also be a 0. So that's the typical situation. We get a certain number of zeros on the actual real line, and then we have a bunch of pairs of complex conjugates, which are also zeros. So let's have a look at an example of this and see how it plays out. So let's start perhaps with a case where we look at factoring something a little bit different from what we just did. Z to the 6th plus 1. Okay, so let's have a look at this little example here where we're looking at factoring z to the 6th plus 1. Let's call it f of z, that one there. All right. Then the zeros are just going to be the solutions to z to the 6th equal minus 1. And we can write minus 1 as, in terms of the polar form, modulus of 1 times e to the I pi, where pi is the argument. Here is the argument. It's that angle right there, right? That's the angle associated to the point minus 1. It's pi. So we're trying to solve z to the 6th equals e to the I pi. We write z equals r e to the I theta as a general complex number in polar form. And then we need to solve this equation that when we raise it to the 6th power, we get e to the I pi. Expand that out. That's the same as r to the 6th times e to the I 6 theta, because the exponent laws work for this complex exponential. That's basically de Moivre's law. And all of that equals e to the I pi. So what can we conclude from all of that? Well, on both sides, the moduli have to agree. So r to the 6th is the modulus on the left-hand side. It has to be equal to the modulus on the right-hand side, which is 1. So we get the equation r to the 6th equals 1. And since r is a positive number, there's only one solution to that, which is r equals 1. What about the modulus? Well, we get 6 theta, which is the argument on the left-hand side, should equal the argument on the right-hand side, which is pi, but possibly up to a multiple of 2 pi. So we write 2 pi k for k some integer. Okay, well, we could rewrite that as theta equals pi over 6 plus, well, 1/3 pi times k. And now we're going to let k run through various possibilities. Okay, maybe I'll do it even in a little organized way here. Okay, here's k and here's theta. Let's have a little chart. Okay, k. So 0, 1, 2, 3, 4, 5. That's really as far as we'll go, because when we get to 6, it'll repeat. Okay, so when k is 0, then what is theta? It's just pi by 6. When k is 1, that's pi by 6 plus 1/3, which is like 1/2, so it's pi over 2. We add another third, so it's 1/6 plus essentially 4/6, so it's 5/6, or 5 pi on 6. We add 3, k is 3, then we're adding pi, so that's 7 pi on 6. And then we add another pi, 9 pi on 6, and 11 pi on 6. Okay. If we added one more, we'd get 13 pi on 6, which is the same as just pi on 6, so it sort of repeats. Now, you have some choice here. These angles are all in the range between minus pi and pi, but these ones are bigger. So we could also write these also by going the other way, essentially subtracting 2 pi. So we could write this as minus 5 pi on 6. We can write this as, that's actually 3 over 2, so it's minus pi on 2, and we can write this one as minus pi on 6. So the solutions are, there's 6 solutions. So the solutions to z to the 6 equals minus 1 are, they are z equals e to the I pi on 6, and I'm going to put the e to the minus I pi on 6 just beside it because, well, those are complex conjugates. So they kind of naturally go together. And then e to the I pi on 2 and e to the minus I pi on 2. Those are also complex conjugates, so why not put them together? And then e to the I 5 pi on 6, positive first, and then e to the minus I 5 pi on 6. And where are these things? Well, they're all on the unit circle, which is something like this. There's minus 1. That's what we're trying to find, the 6th roots of. And the points we get are where? So e to the pi on 6, that's 1/6 of 100 degrees. That's 30 degrees, maybe around there. Okay, so there's e to the I pi on 6. And there's its complex conjugate, e to the minus I pi on 6. And maybe in a different color. Then we have e to the I pi on 2. There's e to the I pi on 2. There's its complex conjugate, e to the minus I pi on 2. And then there's e to the I 5 pi on 6, and its complex conjugate, e to the minus I 5 pi on 6 divided by 6. Okay, so remember we were after the factorization of z to the 6 plus 1, so we can go back to that. So now z to the 6 plus 1 actually factors as a product of, well, all of these different factors. Z minus e to the I pi on 6 times z minus e to the minus I pi on 6. I'm putting the two factors corresponding to the complex conjugates beside each other. That's a good thing. Okay, the next pair, we have z minus e to the I pi on 2 and z minus e to the minus I pi on 2. Okay, good. And two more factors of z minus e to the I 5 pi on 6 and z minus e to the minus I 5 pi on 6. Okay, and if we go back up to the roots here, the zeros on the unit circle, we can also express, for example, e to the I pi on 6, of course, as cosine pi on 6 plus I sine pi on 6, so we can write it in this more familiar root 3 on 2 plus I over 2 form, because we recognize that this little triangle in here is a familiar sort of 1 to root 3 kind of triangle with 30 degrees and 60 degrees. And similarly, we can do that for the other values as well. Now, so we have factored our polynomial into a product of linear factors, and that's what the factorization theorem, that's the consequence of the fundamental theorem of algebra, allows us to do. But in fact, we can actually go further in this kind of situation and sort of remove some of the complex number aspect to revert to something that's purely real. So in other words, if we're just interested in a factorization over the real numbers without any complex numbers at all, then we can obtain that from this kind of factorization simply by writing out the products of these pairs of linear factors corresponding to complex conjugate pairs. So the reason for that is because of this relation right here. If we take z minus w times z minus w bar, where w is some arbitrary complex number, this is z squared minus w plus w bar times z plus w times w bar. And that can be re-expressed as z squared minus this w plus w bar is twice the real part of w. So that's the coefficient of z, minus 2 times the real part of w. And the final term, the constant term, can also be thought of as the quadrants of z, or mod w squared. And the point is, this is a real quadratic. In other words, the coefficients here are all real numbers. So what we've done is we've started with two complex factors corresponding to a complex conjugate pair, and we've obtained one real factor, one real quadratic factor. So we can do this in general. So if we go back to our example of z to the 6 plus 1, we get z to the 6 plus 1 equals, if we put these two factors together, we're going to get z squared minus 2 times the real part, I'll write it out like this, real part of e to the I pi on 6 times z plus, okay, the modulus of e to the I pi on 6 is going to be 1 because it's on the unit circle. Then this one here, well, it's actually z minus I and z plus I. But if we apply the same rule, it would be z squared minus 2 times the real part of e to the I pi on 2. So the real part is 0, so minus 2 minus 0 times z plus 1. And then the last quadratic term corresponding to this pair will be z squared minus 2 times the real part of e to the I 5 pi on 6 times z plus 1. And we can express that in this case a little bit simpler because this is just really a cosine. Okay, so it's really z squared minus 2 times cosine of pi by 6 times z plus 1. So that's the number. That's the factor. And then we have a z squared plus 1. And then we have a z squared minus 2 times cosine of 5 pi on 6 times z plus 1. What are these values of cosine? Well, right here, there's the cosine of pi by 6. And here is the cosine of 5 pi on 6. So we could, if we wanted to, write this factorization as z squared minus just a simple root 3 times z plus 1, because the cosine is root 3 on 2. And then I might bring this other one beside it. Z squared, the cosine in this case is negative, so it's going to be plus root 3 times z plus 1, and a factor of z squared plus 1. So we see a special case of the following important theorem, which is really only approximate. Okay, approximate theorem is that every real polynomial of degree greater than or equal to 1 can be factored into a product of real, linear, and quadratic factors. Okay, so I do want to show you what happens in a special case here, just to solidify what's going on, and maybe also to suggest lots of interesting things that you can actually try to think about yourselves. So if we take z to the 9 minus 1, which is down here, okay, that's corresponding to the 9th roots of unity. Okay, if we factor this, then we see these three factors. Now, according to the theorem I just told you, this actually does factor into a product of linear and quadratic factors. Now, this is already a linear factor, and this is already a quadratic factor. This linear factor corresponds to the 0, which is 1, and this quadratic factor corresponds to the other third roots of unity. So these other 6 zeros here, which are spread around the unit circle, correspond to this fact. That was it. If we just have a look at this by itself, and we set it equal to 0, and we ask for to solve this numerically, then what do we get? I'll put it down here so you can see, hopefully. Okay, can you see that we've got 2 zeros, this 0 here and this 0 here. These are a complex conjugate pair. They're actually on the unit circle, or approximately on the unit circle. And here is another complex conjugate pair, okay? And here's another complex conjugate pair. So let's kind of have a look to see what kind of factors we could get if we looked at some of these. So I'm just going to do the first one. So I'm going to take 2 linear factors, one corresponding to this complex number right here. So I'm going to take this complex number right here, copy it, and put it in here. All right. And then I'm going to take the same thing, but I'm going to adjust it so that this thing here is the complex conjugate. So that instead of having minus 0.642i, it has plus 0.642i. Okay. So I have 2 linear factors corresponding to this complex conjugate pairs. And I'm going to just ask it to expand this. Now, what do we get? Well, you see it's z squared minus 1.532 roughly times z plus 1. And then there's this extra term here, and it's very small because it has a 10 to the minus 30. Where is that coming from? Well, that's just because these values that I put in here were not the exact zeros. Okay, we're not in possession of the exact zeros. We never really are from a computational point of view. So we're always going to get some kind of error. But you can see this is a very small error. It's 10 to the minus 30. So let's just get rid of it and have a look at this. Okay, so this is actually one of the quadratic factors that you get when you expand this out using that theorem that I just showed you. So there's going to be, in fact, 2 other factors like this. Okay, we don't need all these zeros on this one. 2 other factors like this corresponding to the other 2 pairs of complex conjugate zeros. And I'm going to leave it to you to write out the corresponding quadratic factors. But I do want to emphasize here that this is what actually happens in real life. In real life, computationally, okay, this theorem that is a nice theoretical result doesn't actually work exactly in practice. In practice, what you end up getting is approximate linear and quadratic factors. That's just the way the world is. All right, I'll see you next time.